Right now, at this exact moment, the universe is getting bigger. Not slowly, not gently, explosively. Galaxies that are billions of light years away from us are hurtling through space at thousands of miles per second, and the farther they are, the faster they move. The space between everything that exists is stretching, growing, ballooning outward every single second. You cannot feel it. You cannot see it from your backyard. But I promise you, it is happening. And it has been happening since the very first moment of time. And when you truly understand what that means, when you follow that idea all the way to its logical end, what you find is so strange, so genuinely mind-bending that most people never stop to think about it. Today, we are going to think about it all the way through. We are going to talk about whether the universe is infinite, what the mathematics actually predicts about how everything ends, how individual stars can collapse into objects so dense that even light cannot escape, and why time itself, the one thing you thought was constant, actually bends, stretches, and slows down depending on where you are in the cosmos. These are not science fiction concepts. They are not hypothetical. They are physics. Measured, tested, confirmed physics. And once you understand them, you will never look up at the night sky the same way again. So before we dive in, and this is going to be a deep dive if you are new here and you love content that actually makes you think, that takes the biggest questions in the universe seriously and walks through them step by step, hit that subscribe button right now. Join the community. There is so much more where this is coming from. Now let us begin. Let us start with the question I get asked more than almost any other. Is the universe infinite? It is a deceptively simple question. And the honest answer is, we do not fully know yet. The answer depends on things we have not completely pinned down, specifically how much matter exists in the universe, and how strong gravity truly is at the largest scales. But do not let that uncertainty discourage you, because what we do know is extraordinary, and what the mathematics predicts all three possible outcomes is stranger than almost any story ever told. Start here. Right now, as you watch this, space itself is expanding. Not the stuff in space. Not just the galaxies moving through space like billiard balls rolling across a table. Space itself, the very fabric of the cosmos, is stretching. Imagine drawing two dots on a rubber band and then pulling the rubber band from both ends. The dots move apart. Not because they are moving themselves, but because the material between them is stretching. That is exactly what is happening to the universe. The rubber band of space is being stretched, and all the galaxies painted on it are being carried apart as a result. The farther two galaxies are from each other, the faster this stretching carries them apart. A galaxy 1 billion light years away recedes from us at a certain speed. A galaxy 2 billion light years away recedes at roughly twice that speed. A galaxy 10 billion light years away recedes at roughly 10 times that speed. Keep pushing the distance out far enough, and you reach a point where galaxies are receding from us faster than the speed of light. Not because they are moving through space faster than light, that would violate Einstein's rules, but because space itself is expanding so fast that the distance between us and those galaxies grows faster than light can cross it. Those galaxies are beyond our observable horizon. Their light will never reach us. They exist, but we can never see them, communicate with them, or know anything about them. Not ever. Now, here's what makes this deeply profound. If the universe is expanding now, if everything is moving apart, then think about what that means when you run the film backward. If galaxies are moving apart today, that means yesterday they were slightly closer together. Run the film back 1 million years, much closer. 1 billion years, closer still. 10 billion years, incredibly close together. Keep running it back all the way to the beginning and you arrive at a moment when everything, every galaxy, every star, every atom, every particle of matter and energy that has ever existed anywhere in the cosmos was compressed into a single, unimaginably small, unimaginably hot, unimaginably dense point. That moment, that first instant, we call it the Big Bang. And here is something critically important to understand about the Big Bang that most people get wrong. It was not an explosion in space. It was an explosion of space. There was no empty room that a bomb went off in. There was no outside where something could have been watching. Space itself began at that moment. Time itself began at that moment. Everything began at that moment, not just the matter and energy, but the very arena in which matter and energy exists. The Big Bang was not an event that happened somewhere in the universe. The Big Bang was the universe, the beginning of everything. including the concepts of somewhere and when. Now, how did we figure all of this out? Because this is not ancient philosophy. This is modern science, and it has a specific, fascinating history. In the 1920s, astronomers began systematically studying distant galaxies, measuring their light, analyzing their spectra, cataloging their properties, and they noticed something that did not make sense at first. The light coming from distant galaxies was the wrong color. Specifically, it was shifted toward the red end of the spectrum. Red shifted. To understand why this matters, you need to understand a phenomenon called the Doppler effect. You have experienced it with sound. Think about a police siren or an ambulance racing toward you. As it approaches, the sound waves get compressed and the pitch sounds higher than it actually is. As it moves away from you, the sound waves get stretched and the pitch drops. The actual pitch of the siren has not changed. Your perception of it changes because of relative motion. Light behaves the same way. When a light source moves toward you, the light waves get compressed and the light shifts toward the blue end of the spectrum. When a light source moves away from you, the light waves get stretched and the light shifts toward the red end of the spectrum. This is redshift. What astronomers in the 1920s discovered was that virtually every distant galaxy they observed was not just redshifted, but redshifted in a very specific, mathematically consistent pattern. The farther the galaxy, the greater the redshift. The greater the redshift, the faster it was moving away. And this was not a handful of galaxies. It was essentially every single galaxy they looked at in every direction. The universe was not static. It was not stable and eternal. It was expanding in all directions, uniformly. The man most associated with this discovery is Edwin Hubble, and the mathematical relationship between a galaxy's distance and its recession speed became known as Hubble's law. But Hubble did not work in a vacuum. Theorists like Georges Lemaître had already proposed that Einstein's equations of general relativity predicted an expanding universe. Einstein himself had initially resisted this conclusion, adding a fudge factor to his equations to force a static universe. He later called it his greatest blunder. The observational data forced everyone to accept what the math had been saying all along. The universe has a beginning, and it is growing. Now, once you accept that the universe is expanding and that this expansion traces back to a single point of origin, the natural question becomes, what happens next? Does it just keep expanding forever? Or does something eventually bring it to a halt? Or worse, reverse it? And that is where gravity enters the story. Everything in the universe has mass. Every atom, every molecule, every star, every planet, every galaxy. And mass creates gravity. Gravity is not just a local force that keeps your feet on the ground and holds the moon in orbit. It is a universal force. Every piece of matter in the cosmos exerts a gravitational pull on every other piece of matter. And while space is expanding and galaxies are rushing apart, gravity is working in the opposite direction. It is always pulling, always tugging, always trying to draw everything back together. So the critical question becomes, which force wins? Expansion or gravity? And the answer to that question gives us three fundamentally different futures for the universe. To understand this intuitively, think about throwing a ball straight up into the air. The moment it leaves your hand, it is moving upward. But gravity is constantly decelerating it. What happens depends on how fast you threw it. If you threw it slowly, gravity wins. The ball rises, slows, stops, and falls back into your hand. If you throw it at exactly the right speed, what physicists call escape velocity, the ball rises forever, but its upward speed approaches zero over time. It escapes, barely. And if you throw it faster than escape velocity, the ball rises forever with speed to spare. Gravity slows it down, but never enough to stop it. The universe works exactly the same way. The Big Bang threw everything outward. Gravity has been tugging back ever since. Which outcome we get depends on the balance between the expansion rate and the total gravitational pull of all the matter in the universe. The first possibility, the open universe, expansion forever. The first scenario, the universe is expanding too fast for gravity to stop it. The outward momentum is simply too great. Over cosmic timescales, galaxies race farther and farther apart. Star formation gradually slows as the gas and dust needed to build new stars get spread too thin across too much space. One by one, existing stars exhaust their fuel and burn out. Galaxies grow dimmer, emptier. The gaps between galactic clusters grow to incomprehensible sizes. Billions of years pass, trillions. The universe grows colder with every passing epoch. The last red dwarf stars, burning feebly on tiny amounts of hydrogen, finally gutter out. What remains are the cold, dark remnants of stellar corpses, white dwarfs that have cooled to black, neutron stars slowly radiating away their heat. The invisible gravitational sinkholes left behind by the most massive stellar deaths, even these eventually fade or decay over unimaginable stretches of time. The universe does not end with a bang. It does not end with fire or catastrophe. It simply dims, gets colder, gets emptier, approaches a state of maximum entropy, maximum disorder, where nothing interesting can ever happen again. Not because anything destroyed it, but because all the useful energy has been spent. Physicists sometimes call this the heat death of the universe. Not a dramatic ending, just an eternal, frozen silence. # the second possibility, the flat universe, balanced on a knife. A second scenario is the most mathematically elegant and, in some ways, the most haunting. In this case, the universe is expanding at almost exactly the critical rate. Gravity is strong enough to slow the expansion, but only just barely. The universe keeps expanding forever, but slower and slower with each passing eon. Theoretically, at infinite time, the expansion rate approaches zero. The universe balances on a perfect knife's edge between collapsing and expanding freely. This is called the flat universe, because of how the geometry of space works out in this scenario. In a flat universe, parallel lines stay parallel forever. The geometry of space on the largest scales is Euclidean, the kind of geometry you've learned in high school, and the fate of the flat universe is similar to the open universe, though even more precisely balanced. It expands forever, the expansion rate asymptotically approaching zero, but never quite reaching it. Stars still burn out. Galaxies still go dark. The universe still ends in cold, vast, empty silence. # the third possibility, the closed universe, the big crunch. The third scenario is the most dramatic and, to many Piopli, the most philosophically unsettling. In this case, there is enough matter in the universe, enough gravitational pull that expansion eventually stops entirely. The galaxies, which have been racing away from each other since the beginning, gradually slow down. They slow further, they stop, and then inexorably they begin to fall back toward each other. Imagine watching a film of the Big Bang and then pressing rewind. That is essentially what happens in the Big Crunch scenario. The universe begins to contract. Galaxies that have spent billions of years racing apart now begin to approach each other. The distances shrink. Galactic clusters, which were once separated by hundreds of millions of light years, begin to merge. Galaxies collide in slow-motion cosmic catastrophes. Stars are ripped from their orbits. The night sky, which for most of the universe's history has been nearly empty darkness punctuated by distant points of light, grows brighter and brighter as more and more galaxies crowd into an ever smaller volume of space. As the contraction accelerates, the temperature of the universe rises. The cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, gets hotter and hotter as space compresses. Eventually, the universe is hot enough that stars cannot exist, then dense enough that atoms themselves cannot hold together. Electrons are stripped from nuclei. Nuclei are shattered into protons and neutrons. Then even protons and neutrons are crushed into their constituent quarks. Everything that exists, every particle, every quantum of energy, every scrap of matter in the entire cosmos is compressed back into a single, infinitely small, infinitely hot point, a singularity, just like the one we started from. Maybe it stops there. Maybe everything simply ends at that singularity, compressed into nothingness with no after because time itself ends with it. Or maybe, and this is where the mathematics gets truly wild, that singularity is unstable, and the compression bounces back into a new expansion. A new Big Bang, a new universe, beginning from the ashes of the old one. A cyclic cosmos endlessly expanding and contracting. Universe after universe stretching back through time without a beginning and forward through time without an end. We do not know. The mathematics at the singularity breaks down. Our equations stop giving meaningful answers. And that silence at the heart of the calculation is one of the great unsolved problems in all of physics. Now, what is remarkable is that this same drama, expansion versus gravity, the question of which force wins, plays out, not just at the scale of the entire universe, but at the scale of individual stars. And the story of how stars live and die is not just beautiful in its own right. It leads us directly to one of the strangest objects the universe has ever produced. Stars are, at their core, a contest between two forces. Gravity is always trying to compress the star, to crush it inward under the weight of its own mass. Radiation pressure, the energy released by nuclear fusion in the star's core, pushes outward and holds that gravitational compression at bay. For as long as the star has fuel to burn, this balance holds. The star shines steadily, stable, sometimes for billions upon billions of years. Our own sun has been burning for approximately 4.5 billion years and will continue burning for roughly another 5 billion. That is an almost incomprehensible span of time. And yet the sun is a fairly average, mid-sized star. Some stars burn much more slowly and could last hundreds of billions of years. Others, the massive, blazing giants, burn so ferociously that they exhaust their fuel in just a few million years. Fast and brilliant, but brief by cosmic standards. But every star, without exception, eventually runs out of fuel. And when it does, the outward pressure that has been holding gravity back disappears. And gravity, which has been patient, which has been waiting for this moment since the star's formation, finally wins. What happens next depends almost entirely on how massive the star is. For small stars, stars like our sun or smaller, the collapse is relatively gentle. As the core runs out of hydrogen fuel, the star undergoes some dramatic transformations, ballooning outward into a red giant before eventually shedding its outer layers. What remains is the core itself, a dense, hot ball of compressed matter roughly the size of Earth. But with nearly the entire mass of the original star packed into that small volume, this object is called a white dwarf. It no longer generates energy through fusion. It simply glows with residual heat, like a cooling ember. Over trillions of years, it will gradually cool, dimming from white to yellow to orange to red to eventually a cold, dark, invisible sphere floating silently in space. A black dwarf, a stellar tombstone for more massive stars. However, the ending is catastrophic, violent, spectacular, and it leads somewhere genuinely strange. When a massive star exhausts its nuclear fuel, the collapse of its core is not gentle at all. It happens in a fraction of a second. The core implodes with ferocious speed. Electrons and protons in the core are squeezed together so forcefully that they fuse, combining to form neutrons. In the span of moments, the core transforms from a ball of normal matter into a dense sphere, composed almost entirely of neutrons, packed together as tightly as the laws of physics allow. This object is called a neutron star. A neutron star is genuinely difficult to comprehend. It is typically about 10 to 15 miles across, roughly the size of a city, but it contains more mass than our entire sun. The density is absolutely staggering. A single teaspoon of neutron star material would weigh roughly as much as a mountain here on Earth. The surface gravity of a neutron star is so powerful that if you dropped an object from just 1 meter above the surface, it would hit the ground at a significant fraction of the speed of light. The magnetic fields are the strongest in the known universe. Neutron stars can spin hundreds of times per second, beaming radio waves into space with the precision of an atomic clock. We call those pulsars, and they are among the most remarkable objects ever discovered. But here's where the story takes its most dramatic turn. Neutron stars, as extraordinary as they are, have a limit. There is a maximum mass that even the packed neutrons can support against gravitational collapse. This limit, known as the Tolman-Volkoff limit, is roughly 1.5 to 3 times the mass of our sun. Exceed that limit, and even the rigid wall of neutron pressure crumbles. And when that happens, the collapse does not stop. This is where we need to talk about the mathematics, because when physicists take Einstein's equations of general relativity, the equations that describe how gravity curves space and time, and apply them to an object that has collapsed beyond a certain critical density, the equations begin to say something deeply uncomfortable. For every mass, there is a critical radius. Compress any object below that radius. And the equations predict something that looks mathematically like a tear in the fabric of space, a boundary where the normal rules stop applying. This critical radius is named the Schwarzschild radius after Karl Schwarzschild, a German physicist who found this mathematical solution to Einstein's field equations in 1916 remarkable, considering he did the calculation while serving on the front lines of World War I. The Schwarzschild radius depends only on the mass of the object. For something as massive as our sun, it works out to roughly 3 kilometers, about 2 miles. Our sun's actual radius is about 700,000 kilometers. So the sun is nowhere near collapsing into this extreme state. Its actual size is hundreds of thousands of times larger than its Schwarzschild radius. For the Earth, the Schwarzschild radius is about 9 millimeters, the size of a marble. The Earth is obviously nothing like a marble. It is fine. But for a massive star whose core collapses beyond the neutron star limit, the collapse does not stop at the Schwarzschild radius. The collapsing matter punches right through it. And once it does, the equations predict something that has no analogy anywhere in ordinary experience. Below the Schwarzschild radius, the geometry of space changes so completely that there is no direction that points outward anymore. Every possible path, every trajectory a particle could follow, every direction light could travel, leads toward the center. The concept of outward simply ceases to exist. An object that crosses the Schwarzschild radius cannot escape, not because it is trapped behind a wall, but because every road it could possibly take leads deeper in. There is no way out, not through any technology, not at any speed, because there is no spatial direction that counts as a way anymore. We call the boundary at the Schwarzschild radius the event horizon, and we call the collapsed object itself a black hole. Now here is where the story becomes genuinely philosophical and yet completely grounded in physics. Imagine a massive star in the final moments of its collapse. Its core is imploding, gravity is crushing it past the neutron star limit, and imagine, hypothetically, that someone, a brave and doomed observer, is standing on the surface of that collapsing star, falling inward with it, and you are watching from far away, safe, through a powerful telescope. What do you see? At first, nothing unusual. The star shrinks. The surface gets smaller, denser. Your observer falls inward. Light from the surface travels to your telescope, and you see him there, moving, perhaps waving. But as the star approaches the event horizon, something strange begins to happen to the light you receive. It shifts toward the red, not because the observer is moving away from you in the traditional sense, but because light climbing out of an intense gravitational field loses energy in the process. The photons have to work against gravity to escape, and that work costs them energy. Lower energy means longer wavelength. Longer wavelength means redder light. The closer the star gets to the event horizon, the more severe this gravitational redshift becomes. And this is where time enters the picture in a profound way. The same gravitational field that redshifts the light also affects time. Einstein's general theory of relativity predicts, and this has been measured and confirmed, that time runs at different rates in different gravitational environments. In weaker gravity, time runs faster. In stronger gravity, time runs slower. This is not a philosophical statement. It is not a metaphor. It is a literal, measurable, physical fact. As the star approaches the event horizon, the gravity experienced by matter near the surface grows toward infinity. And from your distant perspective, watching through your telescope, the observer's movements appear to slow down. Not a little dramatically. As the star gets arbitrarily close to the event horizon, the observer appears to move more and more slowly, like a film playing at lower and lower speeds. His light grows redder and dimmer, and at the moment the star reaches the event horizon precisely, the observer, from your perspective, appears to freeze completely. His image is locked at the boundary, frozen there for eternity. His clock stopped, his motion halted. This is why these objects were sometimes called frozen stars in early discussions. From your vantage point outside, nothing ever crosses the event horizon. Everything just piles up at the boundary, frozen, increasingly redshifted, increasingly invisible. Now ask the opposite question. What does the observer experience? Nothing unusual. Absolutely nothing. No jolt, no warning, no sign, no physical sensation that anything special is happening. From his perspective, time flows normally. The star collapses normally, and he passes through the event horizon in a perfectly smooth, continuous way in what might feel like seconds or minutes. He does not know the moment he has crossed the point of no return because there is no local sign of it. The event horizon is not a wall. It is not made of anything. It is just a mathematical boundary, a threshold where the global geometry of space changes, but where locally, in the immediate vicinity, space feels perfectly normal. He crosses the horizon, his watch ticks, he breathes, he tries to send a signal back out. He points a flashlight at the outside universe. And the light from that flashlight goes nowhere. It can escape from every photon bends inexorably inward. Every signal he tries to send gets captured by the curved geometry and redirected toward the center. Key is trapped not in a prison with walls, but in a region of space where the geometry itself provides no exit. And he continues to fall toward the center, toward what physicists call the singularity, a point where the mathematics produces infinite density. Infinite curvature in our equations break down entirely. We genuinely do not know what happens at the singularity, whether the concept of a physical point even makes sense there, whether some new physics, perhaps a successful theory of quantum gravity, would describe something more nuanced. We do not have that theory yet. So here is what is remarkable. From outside, the observer is frozen at the event horizon forever. From inside, he crossed the horizon in finite time and continues to fall. Both descriptions are correct. Both are physically real. They are simply two different perspectives on the same event, as seen by observers experiencing time at radically different rates. And neither perspective is more true than the other. This is not a contradiction. It is the actual nature of space-time as revealed by general relativity. If any of this sounds too strange to be real, if the slowing of time sounds like science fiction, let me ground it completely in experiment. Time dilation is not a theoretical prediction that has never been tested. It has been tested many times, in many ways, with increasing precision. And it has never failed to match Einstein's predictions. Consider this. Your head and your feet are at slightly different distances from the center of the Earth. Your head is a little farther away, where Earth's gravity is slightly weaker. According to general relativity, time runs slightly faster in weaker gravity, which means your head is aging slightly faster than your feet right now as you watch this. The difference is extraordinarily small over your entire lifetime. Your head will age approximately 90 nanoseconds more than your feet, but it is real. It is measurable with modern atomic clocks. In 1959, physicists Robert Pound and Glenn Rebka performed an elegant experiment at Harvard University, using the Mix-Bauer effect to measure the gravitational redshift of photons. They sent gamma rays up a 22-meter tower and measured their frequency when they arrived at the bottom. The frequency had shifted because the photons had traveled from a region where time runs slightly faster to a region where time runs slightly slower. The shift matched Einstein's prediction with extraordinary precision. Time runs at different rates in different gravitational fields. This is not speculation. It is measurement. The global positioning system, the same technology your phone uses for navigation, has to account for time dilation every single day to function correctly. The satellites orbiting Earth are in weaker gravity than we are on the ground, so their clocks run slightly faster. They are also moving at high speed, which causes a separate effect, special relativistic time dilation, that makes their clocks run slightly slower. The net effect is that, without correction, GPS clocks would drift by about 11 microseconds per day. 11 microseconds sounds tiny, but at the speed of light, 11 microseconds corresponds to a position error of about 3 kilometers. Uncorrected GPS would be useless within hours. The engineers who designed GPS had to build an Einstein S-time dilation corrections to make the system work. They did. It works. Near a neutron star, the effects are dramatic. Time on the surface of a neutron star runs roughly half as fast as time far away from it. An hour experienced on the surface corresponds to about 2 hours experienced by a distant observer. A hypothetical clock placed on the surface of a neutron star would fall behind a distant clock by 30 minutes every hour. Near the event horizon of a black hole, the time dilation becomes extreme to the point where no simple ratio captures it. An hour experienced by someone hovering just outside the event horizon might correspond to centuries or millennia, or longer for someone watching from a safe distance. And at the event horizon itself, from a distant observer's perspective, time for the infalling observer stops completely. This is not a trick. This is not a visual illusion or a measurement artifact. Time genuinely flows at different rates in different parts of the universe, depending on the local strength of gravity. The universe does not have a single universal clock. It has billions upon billions of clocks, all ticking at slightly different rates, all equally valid, none more correct than any other. So if black holes are by definition dark, if no light can escape from them, how would we ever find one? How would we know they exist? This is a question that has occupied physicists for decades, and the answers are indirect but convincing. We cannot see a black hole directly, but we can see its effects on everything around it. The first approach involves binary star systems. Most stars in our galaxy are not alone. They exist in pairs, or sometimes larger groupings, orbiting their common center of mass in a gravitational dance that can last for billions of years. If one of those stars is massive enough to end its life as a black hole, you end up with an unusual situation. A visible star orbiting something that appears to be nothing, an empty region of space. The visible star follows a curved orbital path around an invisible partner. By carefully tracking that orbit, measuring the visible star's speed and direction over time with precision instruments, astronomers can calculate how massive the invisible companion must be. If that calculated mass exceeds what is possible for a neutron star, and if no light comes from the companion, then the conclusion becomes hard to avoid. The invisible partner is a black hole. Several excellent black hole candidates have been found this way. The system known as Cygnus X1, for example, was one of the first strong black hole candidates identified. A visible blue supergiant star is locked in a tight orbit with an invisible companion estimated to be about 15 times the mass of the Sun, far too massive to be a neutron star or any other known type of compact object. The second approach involves gravitational lensing. Einstein's theory of general relativity predicts that massive objects bend the path of light that passes near them. The Sun bends starlight. This was first confirmed during the total solar eclipse of 1919 in one of the most celebrated experimental confirmations in the history of science. A black hole would bend light far more dramatically. If a black hole passes in front of a distant star, from our perspective, the black hole acts as a gravitational lens, bending the star's light around it. Depending on the geometry, this can create multiple images of the background star, or amplify its brightness, or produce a characteristic ring of light. An Einstein-Ingi if the alignment is nearly perfect. The probability of catching such a perfect alignment on any given observation is small. But with modern sky surveys photographing hundreds of millions of stars repeatedly, the odds become manageable. And indeed, gravitational microlensing events have been observed, some consistent with black holes causing them. A third approach involves gravitational waves. When two massive compact objects to black holes or a black hole and a neutron star spiral toward each other and merge, they release energy in the form of gravitational waves, ripples in the fabric of spacetime itself propagating outward at the speed of light. These ripples are extraordinarily tiny by the time they reach Earth, stretching and compressing distances by less than the width of a proton over kilometers of measurement baseline. But with extraordinarily sensitive detectors, specifically the LIGO and Virgo interferometers, these signals can be detected and analyzed. Since 2015, gravitational wave detectors have recorded dozens of events consistent with black hole mergers. Each detection carries a characteristic mathematical signature that allows physicists to estimate the mass, spins, and distances of the merging objects. The data fits the predictions of general relativity with remarkable precision. Black holes are not just theoretical. They are being directly detected, their properties measured, their mergers cataloged. There is something important to say about the history of how physicists have responded to the strange predictions of general relativity, because it reveals something important about the nature of science itself. When the mathematics of general relativity first began predicting these extreme collapsed objects, many physicists were uncomfortable with the implications. Some argued that nature must have a way of preventing such extreme collapse, that stars would always explode, always shed enough mass, always do something to avoid crossing the Schwarzschild radius. The argument was, because the result is so strange, there must be a physical mechanism that prevents it. But that kind of reasoning is backward. You cannot decide what nature is allowed to do based on what makes you comfortable. You cannot look at an equation that predicts something strange and decide the equation must be wrong simply because the prediction is inconvenient. Physics has a long history of producing predictions that seemed absurd until experiments confirmed them. Quantum mechanics tells us that a particle can exist in two places at once until observed. Relativity tells us that moving clocks run slow. The Big Bang tells us that the universe began. All of these were resisted. All of them turned out to be correct. The right response to a strange mathematical prediction is not to declare it impossible. The right response is to ask, what evidence would confirm or refute it? What observations would we expect to see if it is true? How can we test it? That is science. That is the honest engagement with reality that drives human knowledge forward. And when it comes to black holes, when it comes to the reality of objects so massive and dense, that space itself, curves completely shut around them. The tests have been run. The evidence has accumulated. Gravitational wave detectors have heard them merge. X-ray observatories have watched matter spiral into them in white-hot accretion disks. The Event Horizon Telescope has produced direct images of the shadows cast by the supermassive black holes at the centers of galaxies. The mathematics was right. The universe is stranger than it appears. Space is expanding right now. Every second, the universe grows larger. The galaxies are racing apart, and the farther they are, the faster they go. We know this because of the redshift of their light, the same Doppler effect that changes the pitch of a passing siren applied to light itself. We know that if space is expanding now, then everything was closer together in the past. All of it compressed back to a single moment, the Big Bang, the beginning of space, time, matter, and energy. We do not know how the story ends, whether gravity will eventually slow the expansion to a halt and pull everything back together into a big crunch, whether the universe will expand forever and slowly freeze into cold, dark silence, or whether it sits on the precise knife's edge between those two fates. The answer depends on how much matter exists, how strong gravity really is. And on a mysterious component, we have only recently discovered dark energy that appears to be accelerating the expansion in ways we are still trying to understand. Individual stars live and die by the same drama, gravity versus the pressure of nuclear fire. When the fire goes out, gravity wins. For small stars, the ending is peaceful, a slow, cooling white dwarf drifting through the dark. For massive stars, the ending is catastrophic, collapsing in seconds into neutron stars and, for the most massive, into black holes, regions where the geometry of space curves completely shut, where time slows to a stop from outside and continues normally from inside, where light itself cannot escape. Time is not what you think it is. It does not flow at the same rate everywhere. It runs faster in weak gravity, slower in strong gravity. This has been measured with gamma rays, with atomic clocks, with GPS satellites, with every precision instrument that has been pointed at the problem. Your head ages faster than your feet. Earth's core is younger than its surface. Near a black hole, an hour might correspond to an eternity outside. These are not metaphors. They are the measured, confirmed, reproducible reality of the universe. The mathematics does not care whether we find its predictions comfortable. Einstein's equations do not soften their answers to spare our intuition. The universe is what it is. Our job, the job of every person who loves science, who looks up at the night sky and feels that pull of wonder, is to follow the evidence wherever it leads, even when it leads somewhere strange, especially when it leads somewhere strange, because the strangeness is real. And the universe, the more you understand it, is not less wonderful for being so bizarre. It is more wonderful, incomprehensibly, achingly, beautifully more wonderful. The question of whether the universe is infinite is not yet answered, but the journey toward that answer has already shown us that reality is far richer, far stranger, far more magnificent than anyone imagined before the mathematics revealed it. And that journey is not over. Not by a long shot. If you've made it this far, I want you to know something. You're exactly the kind of person this content is made for. You stayed. You thought. You wrestled with ideas that most people never even encounter, let alone try to understand. That matters. So here's what I am asking you to do right now. If this video made you think, if it changed the way you see the universe even a little bit, hit that like button. It takes 1 second and it genuinely helps more people find this content. You would be helping someone else have the same experience you just had. Leave a comment below. Tell me, which possibility for the universe's fate do you find most compelling? The cold, dark silence of eternal expansion. The perfectly balanced knife's edge of the flat universe, or the dramatic, fiery collapse of the Big Crunch. I read every single comment. I want to know what you think. And if you are not already subscribed, please subscribe right now. Hit the bell icon so you never miss a new video. There is so much more to explore: dark matter, dark energy, quantum gravity, the nature of time, the possibility of parallel universes, the deepest mysteries at the edges of what we know. Every single one of those topics is as rich, as strange, and as mind-expanding as what we covered today. This is what we do here. We take the biggest, hardest, most important questions in science and we work through them together, step by step, with honesty and rigor, and above all, a genuine sense of wonder. The universe is strange. It is enormous. It is beautiful. And we are just beginning to understand it. Let us keep going.